The ground does not send a warning before it moves, and in a single quiet second the illusion of permanence can collapse beneath steel, glass, and human certainty. What feels solid and eternal can suddenly tremble like paper, reminding us how fragile our cities truly are. Across the world, earthquakes have rewritten skylines and shattered confidence, leaving behind images of dust-filled air and streets that no longer resemble the maps we trusted. Entire communities have learned that height and beauty mean nothing if the ground below refuses to stay still. But somewhere on this restless planet stands a different kind of skyline, one built not on denial of danger, but on acceptance of it. In a nation where the earth shakes thousands of times each year, engineers chose not to run from fear, but to design directly against it. Here, skyscrapers are not symbols of arrogance, but conversations with nature, rising carefully from soil that history has proven unstable and unforgiving. This place is Japan, where survival is not luck but structure, and where cities are built with the expectation that the ground will move. Japan rests along the Pacific Ring of Fire, a volatile seismic belt where the Pacific, Philippine, Eurasian, and North American plates converge and constantly press against one another. This convergence creates immense geological tension beneath the islands, making seismic instability a permanent structural condition rather than an occasional disruption. More than 1,000 perceptible earthquakes occur across Japan each year, ranging from faint tremors to destructive shocks capable of altering entire districts within moments. Although most quakes are minor, their sheer frequency reinforces a shared national awareness that stability is temporary and never guaranteed. The Japanese archipelago itself was formed by tectonic collision, meaning the same geological forces responsible for its mountainous terrain and dramatic coastlines remain active beneath its cities. Subduction zones offshore accumulate pressure slowly over decades before releasing energy in sudden movements that can ripple across vast regions. Throughout recorded history, powerful earthquakes have repeatedly destroyed urban centers, reshaping both physical landscapes and national priorities in their aftermath. Reconstruction efforts became recurring chapters in Japan's development, embedding disaster response and structural reform into long-term planning rather than treating them as isolated emergencies. The 1923 Great Kanto earthquake devastated Tokyo and Yokohama, killing over 100,000 people and exposing severe weaknesses in building materials and emergency coordination systems. Its aftermath triggered sweeping reforms in construction standards, urban spacing, and fire prevention strategies. In 1995, the Kobe earthquake struck a modern industrial city and revealed that contemporary infrastructure still contained hidden vulnerabilities under extreme stress. Elevated highways collapsed and residential blocks fractured, prompting another comprehensive review of seismic engineering assumptions and regulatory enforcement. These recurring catastrophes produced not only technical improvements, but also institutional discipline, as building codes evolved through incremental tightening after each major event. Seismic research institutions expanded, simulation models improved, and collaboration between government agencies and private engineers intensified. In Japan, the movement of the Earth is not treated as an abstract scientific concept, but as a measurable design variable embedded directly into architecture and governance. Earthquakes shape policy, engineering, and urban identity, forming the foundation of a national commitment to structural resilience. Japan's relationship with earthquakes did not produce fear alone, but a long-term institutional response that transformed repeated destruction into structured national reform. Survival gradually evolved into innovation as each disaster exposed weaknesses that could no longer be ignored by policymakers and engineers. After the devastation of the 1923 Great Kanto earthquake, authorities recognized that traditional wooden construction and narrow urban layouts amplified both collapse and fire spread. In response, new building regulations introduced stricter material standards, wider roads, and deliberate urban spacing designed to reduce cascading destruction. Post-war reconstruction accelerated modernization, as reinforced concrete and steel frameworks increasingly replaced older structural methods vulnerable to lateral ground motion. Government agencies began integrating seismic data into planning processes, ensuring that rebuilding efforts were informed by measurable geological realities rather than optimism. The 1968 Tokachioki earthquake further revealed structural deficiencies in school buildings and public facilities, prompting nationwide reviews of safety compliance and retrofitting standards. Educational institutions, hospitals, and transportation networks were reevaluated under stricter seismic performance expectations to prevent preventable loss of life. When the 1995 Kobe earthquake struck a highly industrialized city, it demonstrated that economic advancement alone did not guarantee structural resilience under extreme seismic stress. The scale of infrastructure failure accelerated comprehensive revisions to building codes, enforcement mechanisms, and inspection transparency across the country. By the early 21st century, seismic engineering in Japan had become proactive rather than reactive, emphasizing predictive modeling and continuous regulatory refinement. Instead of waiting for catastrophe to dictate reform, research institutions and lawmakers collaborated to anticipate structural vulnerabilities before they could manifest and collapse. This pattern of learning through adversity shaped a national mindset that treats disaster not as fate, but as a technical challenge requiring disciplined response. Innovation in Japan's construction sector emerged directly from accumulated memory, turning repeated vulnerability into a framework for measurable structural advancement. Japan's engineers have developed construction techniques that treat seismic activity not as an unpredictable threat, but as an integral design factor, embedding resilience into every high-rise and bridge. Buildings are no longer rigid monuments, but flexible systems capable of moving with the Earth's unpredictable rhythm. Base isolation technology is now standard in modern structures, using shock-absorbing pads between foundations and superstructures to reduce ground transmission. During tremors, these pads allow buildings to float gently, absorbing seismic energy that would otherwise fracture walls and compromise structural integrity, preserving both property and human life. Flexible steel frameworks provide another layer of protection, bending and swaying under lateral forces rather than resisting rigidly. Columns, beams, and cross-bracing are designed to deform slightly, dissipating energy while returning to their original alignment after each tremor, transforming potential catastrophe into controlled motion. Dampers act like engineered muscles within buildings, converting vibrational energy into heat and reducing oscillation amplitude. Tuned mass dampers, often massive pendulums atop skyscrapers, counteract swaying precisely in real time, a silent choreography ensuring towers remain upright even when the ground below thrashes violently. Bridges are designed with expansion joints and flexible bearings that allow spans to shift independently while maintaining load-bearing continuity. Highway networks, elevated roadways, and rail tracks incorporate movement gaps and vibration-absorbing elements, preventing collapse during quakes and maintaining essential transportation lifelines. Even smaller public structures follow the same principle, combining lightweight materials with engineered flexibility to survive frequent tremors. Schools, hospitals, and community centers are constructed to provide safe evacuation routes and prevent structural failures that could impede emergency response. The result is a landscape where architecture seems effortless, yet every element is calculated to respond dynamically to natural forces. Streets lined with skyscrapers do not appear threatening. Their subtle sway is imperceptible to most observers, but crucial for survival. In Japan, engineering against nature is not decoration but necessity. Buildings breathe with the earth, absorbing shocks, protecting inhabitants, and demonstrating that advanced design can transform vulnerability into resilience, a visual testament to the marriage of science and survival. What happens when the same earthquake hits two different systems built on different assumptions about risk and long-term investment? The answer is not determined by magnitude alone, but by preparation, enforcement, and how seriously each society treats structural vulnerability before disaster strikes. In parts of California, strict seismic codes exist today, yet many older buildings were constructed before modern retrofitting standards became mandatory. When significant tremors occur, structures built under outdated regulations can still suffer severe damage despite improvements in newer developments. Retrofitting in the United States often depends on local ordinances, funding priorities, and property ownership decisions that vary from city to city. This uneven implementation means resilience can differ dramatically within the same metropolitan region, creating structural inconsistency during large seismic events. Japan followed a different trajectory after repeated national disasters exposed the cost of partial compliance and delayed upgrades. Building standards were not only strengthened but systematically enforced, with regular inspections and mandatory revisions applied across both public and private sectors. After the 1981 Seismic Code revision, older Japanese buildings were flagged for evaluation under updated performance expectations. Large-scale retrofitting programs were implemented with government oversight, ensuring that structural weaknesses identified in one disaster were corrected before the next inevitable tremor. When the 2011 Great East Japan earthquake struck with immense force, many modern high-rise buildings in Tokyo remained standing despite violent shaking. While infrastructure damage occurred in coastal areas due to the tsunami, the performance of contemporary skyscrapers demonstrated the effectiveness of decades of incremental engineering reform. The difference lies not in geography alone, but in the discipline of continuous adaptation embedded into national policy. Japan's stricter evolution of building standards reflects a collective decision to treat seismic threat as a permanent design condition rather than a temporary concern. In this comparison, resilience becomes measurable rather than theoretical. The same earthquake can produce different outcomes when one system evolves through enforced reform, while another advances unevenly through decentralized implementation and selective retrofitting. Beneath every modern Japanese skyscraper lies a foundation engineered not just to support weight, but to negotiate with unstable ground. Deep piles extend into firm soil layers, anchoring structures securely while distributing seismic forces away from vulnerable surface materials. These piles are often combined with reinforced concrete mats that spread structural loads evenly across the foundation footprint. By enlarging the base contact area, engineers reduce pressure concentrations that could otherwise trigger cracking or uneven settlement during strong ground acceleration. Between the foundation and the main structure, base isolation systems act as controlled separation layers designed to absorb horizontal movement. Thick rubber bearings and sliding components allow the ground to shift beneath the building while the upper structure remains comparatively stable. As seismic waves travel upward, flexible steel frames take over the task of controlled deformation rather than rigid resistance. Columns and beams are calculated to bend within safe limits, dissipating energy through motion instead of transmitting destructive force directly to joints. When a skyscraper begins to sway, that movement is not failure but performance, carefully predicted through simulation models before construction ever begins. Engineers design acceptable sway limits to ensure occupants may feel motion without compromising structural safety or internal systems. Tuned mass dampers positioned near the top floors counteract oscillation by shifting weight in the opposite direction of movement. These massive suspended systems operate silently, reducing amplitude and stabilizing the tower until seismic energy gradually dissipates. Mechanical systems, elevator shafts, and utility lines are also engineered with flexibility to accommodate controlled structural movement. Expansion joints and sliding connectors prevent ruptures in plumbing, electrical conduits, and communication networks during intense shaking. Inside the skyscraper, resilience is layered from the ground upward, combining anchoring depth, isolation technology, flexible framing, and vibration control. The result is a structure that sways with intention, transforming violent ground motion into measured, survivable movement. Much of Japan's seismic innovation is invisible to the casual observer, embedded quietly within walls, ceilings, and mechanical cores of ordinary-looking buildings. What appears architecturally simple often conceals complex monitoring systems designed to measure, interpret, and respond to ground motion in real time. Advanced seismic sensors are installed throughout high-rise structures, continuously collecting data on vibration, displacement, and structural stress. These instruments transmit information to centralized monitoring platforms, allowing engineers to assess performance immediately after an earthquake without waiting for visible damage. Smart building management systems integrate seismic data with automated safety responses to minimize secondary risks during strong shaking. Elevators halt at the nearest floor, gas lines shut off automatically, and emergency lighting activates within seconds of abnormal motion detection. Across major cities, dense networks of ground-based seismographs provide early warning signals before strong shaking fully arrives. When primary waves are detected offshore, alerts are broadcast through mobile devices and public systems, offering crucial seconds for individuals and infrastructure to prepare. Rail networks are directly connected to these early warning systems, enabling high-speed trains to decelerate automatically when seismic activity is detected ahead. This integration of geophysics and transportation engineering reduces derailment risk and demonstrates how data flows through interconnected urban systems. Even residential buildings incorporate simplified seismic countermeasures, such as reinforced joints, flexible piping, and lightweight materials chosen for controlled performance. These design decisions may go unnoticed visually, yet they significantly reduce the likelihood of catastrophic structural failure. Post-earthquake inspection technology has also evolved, using drones and digital modeling to evaluate structural integrity quickly and efficiently. Engineers can compare sensor data with predictive simulations, determining whether a building remains safe for occupancy without prolonged uncertainty. In Japan, technology operates quietly in the background, transforming cities into responsive systems rather than static constructions. The true strength of these urban environments lies not only in visible engineering, but in the hidden intelligence that anticipates and absorbs the Earth's movement. Engineering alone cannot guarantee survival, which is why Japan integrates human preparedness into its national seismic strategy with equal seriousness. Structural resilience is reinforced by behavioral discipline, ensuring that citizens understand how to respond the moment the ground begins to shake. Earthquake drills are conducted regularly in schools, offices, and residential communities, simulating realistic emergency conditions rather than symbolic exercises. Students practice protective positioning, evacuation routes, and coordination procedures until responses become instinctive rather than hesitant reactions. Public awareness campaigns distribute clear guidance on emergency kits, safe shelter zones, and post-quake communication protocols. Television programs, mobile alerts, and community workshops reinforce consistent messaging so that critical information remains familiar long before any crisis occurs. Corporate safety culture plays a significant role in preparedness, particularly within high-rise office environments concentrated in major cities. Companies maintain structured evacuation plans, conduct internal drills, and designate trained floor wardens responsible for guiding employees during emergencies. Disaster readiness extends into household planning, where families are encouraged to store water, food, flashlights, and battery-powered radios. Local governments distribute hazard maps outlining flood zones, evacuation centers, and predicted shaking intensity for specific neighborhoods. While many earthquake-prone regions worldwide promote preparedness, participation rates and enforcement vary depending on local policy and funding priorities. In Japan, drill participation and compliance are normalized through education systems and workplace expectations, creating broader consistency. Media coverage of past disasters reinforces collective memory, ensuring that historical lessons remain present in public consciousness rather than fading into abstraction. Survivors' experiences are incorporated into training materials, strengthening generational awareness of realistic risk. In Japan, seismic resilience is not confined to steel and concrete, but extends into daily behavior and institutional culture. The human factor transforms engineered protection into coordinated response, ensuring that when structures perform as designed, people do as well. On March 11, 2011, a magnitude 9.0 earthquake struck off the northeastern coast of Japan, generating one of the most powerful seismic events ever recorded. The rupture lasted several minutes, releasing immense energy that tested the full capacity of modern engineering systems. In Tokyo, hundreds of kilometers from the epicenter, skyscrapers swayed dramatically yet largely remained structurally intact. Base isolation systems and flexible steel frameworks performed as designed, preventing widespread collapse despite prolonged and intense ground motion. Seismic sensors embedded within buildings transmitted real-time performance data, allowing engineers to evaluate stress distribution immediately after the shaking subsided. Preliminary assessments indicated that most contemporary high-rise structures had absorbed and dissipated energy within predicted safety margins. However, the earthquake triggered a massive tsunami that overwhelmed coastal defenses and devastated communities in the Tohoku region. While many buildings survived the shaking itself, flooding and infrastructure loss revealed vulnerabilities beyond pure structural design. Transportation systems in major urban centers automatically slowed or halted within seconds of early warning detection. High-speed rail networks avoided catastrophic derailments, demonstrating the effectiveness of integrated seismic monitoring and automated response protocols. Post-event analysis showed that buildings constructed under post-1981 seismic codes significantly outperformed many older structures. Retrofitted properties also displayed improved resilience, confirming the long-term value of incremental regulatory tightening. International observers studied the performance of Japanese skyscrapers closely, comparing outcomes with damage patterns seen in other global seismic events. The data reinforced the importance of strict enforcement, continuous updating of codes, and nationwide consistency. The 2011 disaster did not eliminate loss or suffering, yet it validated decades of structural reform within Japan's urban cores. Engineering systems functioned under extreme conditions, proving that disciplined preparation can meaningfully reduce catastrophic collapse even during unprecedented earthquakes. Tokyo's newest megastructures are designed with performance expectations that exceed current seismic minimums, anticipating stronger and more complex ground motion scenarios. Engineers now simulate multi-hazard events, combining earthquake stress with wind loads and long-duration shaking to refine structural response models. Advanced composite materials are increasingly integrated into high-rise construction, offering greater flexibility while maintaining load-bearing strength under repeated stress cycles. These innovations reduce structural fatigue over time, ensuring that buildings remain resilient not only during one major event, but across decades of seismic exposure. Climate adaptation has also entered the engineering equation, particularly as rising sea levels and extreme weather compound coastal vulnerability. Flood barriers, elevated mechanical systems, and waterproofed infrastructure are incorporated alongside seismic reinforcements to address overlapping environmental risks. Urban planners now evaluate infrastructure as interconnected systems rather than isolated structures vulnerable to cascading failure. Power grids, communication networks, and transportation corridors are designed with redundancy, preventing localized damage from escalating into citywide paralysis. Other earthquake-prone nations increasingly study Japan's regulatory model and technological integration for practical lessons. Delegations of engineers and policymakers examine how strict enforcement, consistent retrofitting, and public awareness programs combine to create measurable structural reliability. The future of survival in Japan is not defined by eliminating earthquakes, but by refining response to them through continuous innovation. Each new tower and transit hub reflects accumulated knowledge, projecting resilience forward as a deliberate national commitment rather than a reactive adjustment. Across these cities of steel and glass, resilience is not accidental, but engineered through memory, regulation, and relentless refinement. Japan's skyline stands as evidence that survival can be designed deliberately when a nation chooses preparation over complacency and discipline over temporary convenience. Earthquakes will continue to strike, and the ground will never promise permanent stability to those who build upon it. Yet the lesson here is clear: adaptation, enforcement, and long-term thinking can transform unavoidable risk into structured resilience measurable in steel and survival. If this exploration changed the way you see cities and the hidden systems beneath them, consider supporting Asia Within by liking this video and subscribing for deeper analysis. Share it with someone who believes infrastructure is ordinary, because sometimes the most powerful stories are built quietly beneath our feet.